For our first example, you'll see that I added in some information down here at the bottom so that we can make some calculations. So the cart has a mass of 0.5 kilograms, the spring constant is 2,000, and it's compressed 10 centimeters over here. And the cart is moving at 5 meters per second, and I'm saying right here it's moving at 5 meters per second, and we want to know how high does the cart get above the ground. Well, US is elastic energy, which is 1/2 kx squared. Right? Kinetic energy is 1/2 mv squared, and gravitational potential energy is mgh. So I know that K is the spring constant, and it says here that it is 2,000 newtons per meter. We know that it was compressed 10 centimeters. That's in the wrong units, so I'm going to change that to meters. So that's 0.1 meter, and remember, you've got to square that value. It was given to us that when it's up here at position B, it's moving at 5 meters per second. So the mass of 0.5 kilograms, right, is moving at 5 meters per second, and we want to know how high it gets. The mass of the cart is 0.5. G is the acceleration of gravity, and energy is scalar, so I'm not going to do like a negative or anything like that. And we're looking for H. So when you go to your calculator and you punch in 0.5 times 2,000 times 0.1 squared, you get 10. So your system, your cart earth spring system, had 10 joules of energy when it started. Now, that was weird. The other thing's not moving, but okay. So at the end, in position B, it's going to continue to have 10 joules of energy. So we're going to figure out how much kinetic energy. 0.5 times 0.5 times 5 squared gets us 6.25 joules of kinetic energy. Well, that means that there has to be 3.75 joules of gravitational potential energy. So 0.5 times 10 is 5, and so we can therefore solve for our H, right? We're going to do 10 minus 6.25. So there has to be 3.75 joules of gravitational potential energy. When I divide by 5, it gets me a height, and our cart got to 0.75 meters above the ground at its highest point. Not sure what's going on with that random thing there in the middle, but we'll move on here. Hopefully we can ignore it somehow. Not sure how to get rid of it. So assuming you guys can see the same thing I am, we're ignoring that. Okay, so our part C says use the same system. It says the cart has a mass of 0.5, the spring constant is 2,000, it's compressed 10 centimeters. If the car is moving at 3 meters per second when it reaches a height, the same height that we found in part A, that 0.75 meters, how much energy was lost to friction? So the kinetic energy is the same, right? It's the same spring in the same amount. So our elastic energy is still, right, those 10 joules that we found up there at the other part. So we've got 10 joules of energy minus the work done by friction, and that's what we're looking for in this case, equals our 1/2 mv squared. So 1/2 times our mass times our velocity of 3 squared, right? It's going slower because it's lost some of its energy. And if it is at the same height as before, then our mass of 0.5 times 10 times our height that we found of 0.75, right? That's how high it was. So solving for all of those, you get that we started out with 10 joules of energy, right? The kinetic energy has decreased, so 0.5 times 3 squared gets us that there is only 2.25 joules of kinetic energy, and 0.5 times 10 times 0.75 is that same amount that we had before, 3.75 joules of gravitational potential energy. So because we only end with, what's that, 3, 4, 5, 6 joules of energy, right? And we started off with 10 joules, well, then we lost 4 joules of energy because friction was doing work. Hope that one helps a little, and there are 2 more to come if you want to watch those.